So we're looking at another example of spring energy, and this has not just a spring, but it also has some friction, and then it has some circular motion because this object is going to go over a hump. So here's the setup. We're going to have a horizontal surface, which is initially frictionless, and there's a spring here. So I'm going to draw a wall to squish the spring against. And here is the spring. And we're going to take this box and press it against the spring. So there's a current position of the end of the spring, and then there's a natural length where the spring wants to be. And that amount of spring compression is what I call the variable x sub s. I think our book tends to just call it x. So here is x sub s is the initial compression of the spring. And one thing we know about, actually, it would be better just to call this the spring compression because it's a value that can change. One thing we know about springs is they produce a force, which is minus k x sub s. The minus sign symbolizes the idea that if x sub s is toward the left, the spring force is toward the right. And the amount of force is proportional to the amount of stretch or compression. And the other thing we know about springs is they provide a potential energy function, U sub s, which is minus the integral of k x sub s dx sub s. And that turns out to be 1/2 k x sub s squared. We could add a constant, but we don't care about the constant. And that's what we are going to care about in our situation is the 1/2 kx squared. So now going down the path here, this 2 kilogram mass is going to hit a rough patch. And here there is mu equals 0.4 and delta x equals 0.5. So that's going to go from there to there. Use outside arrows on that one because I didn't give myself enough space. And then after that, our thing is going to go over this little hump. So our surface is now back to its smooth, frictionless self. There is a radius, and then there is a height equals 0.1 meters. And the radius is 10.0 meters. And by the time our box gets here, this is the danger time. So we require that the normal force exists so that that box is remaining in contact with the hump. So when we think about energy, we're always going to try to think about initial plus work equals final. And initially, the only energy we have is our spring energy. So I'm going to put in a 1/2 k x s squared. Our work is the work due to friction. And our work due to friction is minus the force of friction times delta x. Work is generally average force times distance. It's negative in this case because the motion is toward the right while the force of friction is toward the left, opposing it. And we could do a little force diagram here, and it would end up telling us that the force of friction is just mu times mg times delta x, because that was part of the formula. So we have minus mu k times m times g times delta x. So that's what gets taken away from our energy during the process. Now we have the final state. Final state, we're going to have kinetic energy. So we're going to have 1/2 mv squared. But we're also going to have plus mg. We're going to have some gravitational potential energy at the end. So now it's up to us to figure out as much as we can about the terms in this equation so that we can learn the ultimate question, how much initial spring compression, so that's xs equals question mark. So we don't expect to know xs, x sub s from this analysis, but we expect to know everything else. So let's start plugging numbers in. The friction is the easy one. That's minus 0.4 times 2 kilograms times 9.8 times our 0.5. We'll get to this one. We'll get to the 1/2 mv squared. Let's do the mgy. That's 2 kilograms times 9.8 times the height is 0.1. That's our final y value. So that gives us numbers for that. And in the initial one, we're going to have 1/2 times 300 times x sub s squared. Now we have to figure out one more thing. How much kinetic energy are we allowed to have at the top of this hump? And to figure that out, we need to think about our force diagram. We're going to have F sub g and F sub n. And at this point, we have a centripetal. There is acceleration of our block there because it's heading in a circular path. So when we put those together, we get F sub n minus F sub g equals m a centripetal y component. So this will be F sub n minus mg equals minus mv squared over r. And to figure out the threshold condition, to figure out how much is allowed, we'll set Fn equals 0. The minimum possible energy at the beginning will lead to the the maximum possible energy at the beginning lead to the maximum allowed velocity here, to the minimum allowed normal, which is 0. We'll cut that out there, and we get minus mg equals minus mv squared over r. Now, we don't want v. We don't want v squared over r. We want 1/2 mv squared. So let's see if we can make the right hand into 1/2 mv squared. We'll multiply both sides by r. Mg r equals, leave a space there, mv squared. And it almost looks like 1/2 mv squared. All we need to do is multiply both sides by 1/2. And what do you know? We have a formula for the kinetic energy. in terms of given values. We know the mass, we know g, and we know the radius of curvature. So we'll just put in 1/2 times 2 times 9.8 times 10. Now we're down to an equation where we know everything except one variable. And I actually want to calculate these individual terms because amounts of energy mean something to me. So 0.4 times 2 times 9.8 times 0.5 is 3.92. So this green term is minus 3.92 equals the red term is 1/2 times 2 times 9.8 times 10 is, of course, 98. I probably could have done that in my head. And then the black term is 19.6, that's 1.96. And that is going to equal our U sub S. So we start out with a lot of energy. We lose 3.92 joules due to the friction along this skid pad. And then the remaining energy, some of it is used to raise the block up a tiny little bit. But the rest is kinetic energy. So I can take my 98 plus 1.96 and then add my 3.92 joules, and I got 103.88. So this boils down to 1/2 times 300 times xs squared equals 103.88. So that means that xs, my initial spring compression, is 2 times 103.88 over 300. That would leave me with xs squared, so I will take a square root of it. So now I have the square root of 2 times 103.88 divided by 300 is 0.832. Or 83.2 centimeters. And that solves the question. So I just want to quick review the energy accounting of what happened here. We started with 103.88 joules of energy. We didn't know that right away, but eventually we found that out. Of that, 3.92 joules were lost to friction. So that was work due to friction was negative 3.92 joules. And the remaining 99.96 joules were divided between 1.96 joules to raise the mass by 0.1 meters and 98 joules of kinetic energy. So that finishes this example.